In chapter 11, we're going to talk about goodness of fit and also test for independence and homogeneity. So these are some fancy ways of saying, does our data fit what we thought it should be? And that's kind of what or if two variables actually are related. So we're going to look at this. This is from 11.2, number 2, and it's showing the frequency of births on the day of the week. So you can think of it as, does it really matter what day of the week it is, how many births there are going to be, or does this distribution of births over here actually fit what I would expect them to be? Well, I would expect them to be the same every day, which is a uniform distribution. So you kind of say my null hypothesis is the distribution of births fits. The alternative hypothesis is it doesn't fit. At least one or more days is significantly different. So the question is, how do we measure the variation from what we thought it should be? And this is with the chi-squared table and statistics. So if you have your formula sheet, this is the chi-squared distribution. It's a little bit different in that it looks kind of approximately normal, but really what you're looking at here is the spread of data based on degrees of freedom. It's just like the t-table, where the shape of this curve changes depending on how many degrees of freedom you have. In this case, we had 7 days in the week. Degrees of freedom is whatever the number of categories is minus 1, or cells minus 1. So we'd be looking in row 6 for this problem right here. We'd be looking right there in row 6. And you can kind of see these probabilities up here. So this is very similar to our t-table, where we're going to actually calculate a new thing called the chi-squared statistic. And this is a new stat we're going to use to measure essentially variation. So we just need to figure out what did we observe, compare it to what we expected, and then we square those differences, and then we divide it by what we expected, and then we're going to add all those up. So we're going to add up all of those calculations. So I'm going to go back here to the notes, and that's actually, if I was going to show this by hand, I just found the average for the group because they should all be the same. So I actually loaded this in StatCrunch and said, hey, find the average, and it was 55.86. So we would expect 55.86 bursts per cell. That's the average if it was uniform or the same. So what we're going to do is take 50 minus 55.86, find that difference, square it, and divide it by what we expected, which is 55.86. And that's going to be our first part of the chi-squared statistic. We're going to do that for each cell. Observed minus expected, square that difference, divide it by what we expected, and then we're going to add all 7 of these up. And if we do that, and you can do that by hand as well, you're going to get 11.33 essentially. So 11.33 is our chi-squared statistic, which honestly means nothing to you. But if we look at that compared to the distribution that has 6 degrees of freedom, we can say, what's the probability that we get this much variation right here by random chance? And it looks like there's about a little under 8% chance of getting this much variation just by randomness. So the question is, do I reject or not reject my null hypothesis? Well, it looks like our significance level here was 0.05. So we need to experience something that has a probability of happening less than 5% chance. Well, our p-value here is greater than 0.05, so we do not reject the null hypothesis. There isn't significant evidence that that there isn't a uniform distribution here with births. Even though we don't experience it, the question is, what do we practically experience? Does that enough evidence to refute essentially what we think should be going on? And if you notice here, Saturday and Sunday have kind of the lowest numbers, which would cause the most variation. Well, a lot of induced laborers are not scheduled for the weekends, so that might explain that, but still doesn't give us enough data to reject the null here. Here's another one with birthdays. These are Academy Award winners, and our null hypothesis is it doesn't matter what month you're born in, they should all have the same number of Academy Award winners, but obviously there's not. So the question is there a significant variation in this data from what we expect. Again, we should expect they used to be the same, a uniform distribution. So our null hypothesis, all the same. Alternative, at least one of these is significantly different. And so I just loaded this thing in StatCrunch, and if I load that in StatCrunch, hold on here. If I load that in StatCrunch and go goodness of fit, here we go. I'm gonna just go ahead and pop StatCrunch open here, even though it's not this data. All the buttons you do to have to push to do a goodness of fit calculation is load the data up, put your expected values in, and then see how much variation. So it's under stat, goodness of fit, chi-squared. You got your observed values, which whatever row that is, and then you've got your expected values. So you're going to actually type in the expected values by hand here. In fact, why don't I just go back to that one here in 11.2. So if I go back here to 11.2, it's going to make me log in. Hold on. All right, so here's 11.2, and let's look at number 2 here. So you can do these by hand, like this one, and I'll go to number 3 here maybe. Yeah, so we could load all these in by hand and go, okay, how many are there total, what the average, and then figure out how far these are, square those differences, divide by what we expected, and just add that up for all these. But if we go ahead and open in StatCrunch, and then we type in the expected value for each cell manually, that's all we'll need. We'll just need the observed and the expected for every cell, and we'll be good to go. So hopefully that's loading up here. There we go. So there is what we observe. The question is what we expect. So if I go stats, summary stats, columns, number, calculate. So we would expect 18 to be in every one of these. So I'm just going to manually just put 18, and since I'm lazy, I'm going to say copy, and then I'm going to go paste, enter, paste, enter, paste, enter, paste, enter, paste, enter, paste, enter. I wish they had to fill down. Paste, enter. There. So there's our observed frequencies of Academy Award winners, female winners, and then here's the expected. They should have all been the same. Obviously, there's variation. The question is, it's significant variation. We can do goodness of fit, chi-squared. Our observed was in number. Our expected was in bar 3, and we calculate. And there we go. We get a chi-squared statistic of 15.33, and then we get a p-value of about 16%. So there was 12 months, 11 degrees of freedom. And if we pull up our table, if we look at 11 degrees of freedom, and what was our stat again? Like 15 or something like that. It was definitely, if you look here, it was below all of these chi-squareds. So according to this table, we know the probability is greater than 10%, but StatCrunch just straight up tells us, oh, it's right here. StatCrunch just tells us it's 16%, so it's actually way more accurate to use StatCrunch, but our table can just say, hey, it's greater than 10%. Either way, I know I don't have enough evidence to reject the null. There's not significant evidence that it is different. And then the last part that I think is a little tricky on 11.3 is when we start adding two variables together. So if we go on to where we have two variables, in this case we're looking at were the subjects intoxicated or not, and what was their breathalyzer? Did it indicate that they were intoxicated or not, and if they really had alcohol or not? So before, we'd only look at one variable, like birth month. This one's actually looking at two different measurements, and now we have a table of values. So this is like our first kind of jump into analysis of variance and things like that. So the formula is the same. You want to take what's your observed minus what you expect, square it, divided by expected. So the question is, how do you find out what you expect here? And the way you do that is you take row total So in this row total here was what, 61%, 71 times column total, which is 75, divided by grand total, which is 92. So the expected value for this cell is 71 times 75 divided by 92. And do that for each one. For this one, it's 71 times 17 divided by 92. This one here, 21 times 75, 21 times 75 divided by 92. And on this one, 21 times 17 divided by 92. So here's the red are the expected, and then here's the observed. So this is, here's observed minus expected squared divided by expected. Observed minus expected squared divided by expected. And we get a chi-squared statistic of 3.98. And if you look at your table, it says, how do you do when you have a table? Degrees of freedom is rows minus 1 times columns minus 1. So this is only a 2 by 2 matrix. So we get 2 rows, 2 columns. 2 minus 1 is 1, 2 minus 1 is 1, 1 times 1 is 1. So there's only 1 degree of freedom here. And if we look in row 1, 3.98 puts us somewhere between 2.5% and 5% chance. And since our alpha level is what? 0.05, we we do have evidence to reject the null. The null is that these two variables are independent. They don't affect each other. The alternative is that they are dependent. And honestly, being intoxicated and whether your breathalyzer indicates you're so, that should be dependent. So we got a result here. It says, yes, let's reject the null. These things are not independent. They are dependent because our p-value was less than 0.05. Reject the null. Breathalyzer test results is dependent on being intoxicated. So this is what we call test for independence. So really these are the only types of problems they have in Chapter 11. It's a new distribution, I know. It's a new way of calculating expected value. But on your tests, I'm going to probably say, hey, how do you find this expected value? Or here's the chi-squared statistic. Figure out what's the probability. Use the table to find your p-value. And you have to know how to find degrees of freedom. So this table is on your test. You'll have this formula. The only thing you won't have is to find the expected value for a table of values, which is row total times column total divided by grand total. So there's your Chapter 11 video. Obviously, go through, do your homework problems, and there will be a few problems on the final related to this.